In this video, we go for the example 13, where in this example, we will learn on the upper limit for heat transfer in a heat exchanger. So basically, this example is falls under NTU method. So this is the question. Cold water enters a counterflow heat exchanger at 10 degrees Celsius at a rate of 8 kg per second, where it is heated by a hot water stream that enters the heat exchanger at 70 degrees Celsius at a rate of 2 kg per second. Assuming the specific heat of water to remain constant at Cp equal to 4.18 kJ per kilogram dot Kelvin, determine the maximum heat transfer rate and the outlet temperatures of the cold and hot water stream for this limiting case. So from here we can actually find the properties of the specific heat of water, and we know that in this question we already been given with a specific heat of water, okay, which is Cp equal to 4.18 kilojoule per kilogram dot Kelvin. So now what we are going to find is the maximum heat transfer rate. Okay, this is the figure of this question. Okay, we have hot water at 70 degrees Celsius with a flow rate of 2 kg per second, and then we have cold water 10 degrees Celsius and then 8 kg per second. So first and foremost, we have to understand what kinds of method that will be used in order for us to determine what is the heat transfer rate, and then the other one is the temperature outlet for the cold and hot water. So we have two different types of method, okay, two different methods in the heat exchanger. One is LMTD method, second is NTU method. So which of these two will be used, okay, method will be used in order for us to solve this question. So what we have to understand is when we are dealing or we want to use the method of LMTD, so we have to understand that all the temperature, inlet and outlet must be given. Now, take a look at this question. We do have hot water temperature inlet and we have cold water temperature inlet. But we, in this question, outlet temperature for both of these outlet will remain unknown. So that is our job and that is our task to determine what is the T outlet for the hot water and cold water. So in this case, we cannot use LMTD method since we are not being given with all the information, especially for the temperature. So now we will use the NTU method in order for us to solve heat transfer rate and temperature in outlet for both cold water and hot water. So now in NTU method, we know that what we have to calculate is, okay, from here we have to we know that the Q can be found by using Q equal to CC, okay, TC out, okay, minus TC in. And then we have another Q equation, Q dot, we have to use CH equal to TH in minus TH out. Okay, so CC is represent, this is capital C, which is specific heat capacity of cold water times with the mass flow rate. If we want to calculate Q dot, we have to use mass flow rate of cold water. Whereas for the CH, capital C, for hot water, so this is heat capacity, and then this is a lowercase where this is represent specific heat capacity. So to find heat capacity of hot water, so we have to multiply, specific heat capacity of hot water times with mass flow rate of hot water. So that is two different equations where we have to use CC and CH. So we do have another equation where we will find what is the Q maximum. So from here, Q maximum is C minimum times with the H in minus the C in. So cold water is always lower in temperature compared to hot water. That's why hot minus cold water, this will result you with a positive number. So what about the C minimum here? C minimum here is based on these two equations. Okay, CC and CH. C minimum is heat capacity minimum. From these two values, you have to compare which is much more lower than the others. So for example, if you calculate CC for about 400, for example, and then CH is 500. So from these two values, you will select this as your minimum C, where this is the maximum C. So in order for you to substitute into this Q dot maximum, you have to use C minimum. Okay, this what we call as a C minimum. So you will substitute 400 into this equation, and then you have to calculate what is the Q maximum. Okay. So we have another equation where we will use effectiveness, because this method is NTU effectiveness NTU method. So effectiveness is Q dot over Q dot maximum. Okay. So now I will explain about this C minimum. So why do we choose a C minimum as to find what is the maximum Q dot, maximum rate of heat transfer? So you can imagine there is two glass. Okay, you have two glass which have a different volume. Okay, and you are required to choose either one of these to fill up with the water. So for example, this is 500 ml, and then this is 1000 ml. So if you choose that 1000 ml will have full volume, okay, 1000 ml, and then when you want to pour into the 500 ml, and it will go out, another 500 ml will be this space will do not have sufficient space to sustain 1000 ml. Therefore, only 500 ml will be saved when you pour your 1000 ml water into 500 ml, and you will waste 500 ml to the table or surrounding. Okay, so what we are going to do is, from here we know that 500 ml is the minimum volume, And then if you choose 500 ml will fill up with the water, and then if you want to transfer into 1000 ml, it will have enough space for 1000 ml container, this glass, to sustain 500 ml. Therefore, that is the maximum amount of volume that can be transferred between these two glass without loss to the ambient or to the table. So the same concept applies to this C minimum. So if we choose the maximum, when we compare 400 and 500, we chose 500. This 400 will do not have sufficient space to sustain 500 in its container. Okay, and then 100 ml will be wasted. 100 will be wasted. So which means that this could not sustain 500 CH. Okay, so what we have to do, the maximum rate of heat transfer that can be transferred from CC to CH is the minimum. Okay, the minimum where, like this, 500 can transfer without losses to the ambient or table. Okay, that's why C minimum here we are choosing minimum C here. To find the maximum, we have to choose the minimum value CC and CH. Okay, so that's why we have to choose C minimum. So what about TH in and TC in? So for example, we have TC in for about 10 degrees Celsius and TH in is 70 degrees Celsius. The maximum of hot water can be reduced, the minimum temperature that the hot water can be reduced is up to 10 degrees Celsius only. It will not reduce lower than 10 degrees Celsius. Okay, because we know that that amount of energy is only up till 10 degrees Celsius. Okay, it can reduce up to 10 degrees Celsius. So 70 degrees Celsius can only reduce up to 10 degrees Celsius. It will not reduce much more further, much more down than 10 degrees Celsius. So therefore, 70 degrees Celsius can be reduced up to 10 degrees only. So if it is possible, then the hot water will reduce up to 10 degrees Celsius. And then what about the cold water? Cold water can maximum increase up to 70 degrees Celsius. This is the maximum temperature that this can that the hot water can be reduced. So that's why we have to calculate what is the Q maximum. So that is the maximum. Okay, it is not the actual, but it is a maximum that this system can go. Okay, the rate of heat transfer of this system can go. Okay, more to approximate rate of heat transfer at maximum. Okay, now in this case we are not using effectiveness, since we are only calculating what is the Q maximum and then what is the TH out and TC in. Therefore, when we know, we will use the temperature from the Q maximum and we will substitute into these two equations. So in these two equations, we will use the Q maximum. It is actually when you can calculate what is the Q dot, therefore you can actually find what is the Q actual. These two equations represent an actual value of rate of heat transfer. So now in this case, we are not being given with the TH out, and we have to estimate what is the value of T cold out and TH out. Therefore, we have to equate this equation to the Q dot maximum. If possible, if the question provides you with enough information, and then you can actually calculate what is the Q actual. Normally, in the NTU method, you will not be given only one outlet, temperature outlet. Maybe the hot water temperature outlet or cold water temperature outlet. So in this case, both of these temperature outlet was not being given. And then what you have to do is you have to equate those Q values, okay, these Q values to Q dot maximum. Now we have to find what is the Q maximum. So first, in order for you to determine what is the Q maximum, you have to check which of the heat capacity has the minimum value. So either it is a CH or C. Now we calculate what is CH and what is CC. So CH is M dot H. You have to times with CPH, specific heat capacity for hot water. So now when we calculate this, we have 2 kilogram per second times with the specific heat of water, okay, dot Kelvin. You will get this value is 8.36 kilowatt. Okay, do we have any information? So assuming that specific heat of water to remain constant, which means you will use the same specific heat capacity of water for the cold and hot water, okay, with the specific heat capacity equal to 4.18. Now, for the cold water, M dot cold times with CP cold, we have 8 times with 4.18 kilojoule per kilogram dot Kelvin. So you will get this value is about 33.4 kilowatt per Kelvin. Okay, this is kilowatt per Kelvin. So from these two values, we have to compare which of these two values has the minimum value. So from here, we know that 8.36 has the minimum value. So therefore, in the Q maximum, you will use CH as your C minimum. So here you substitute CH, TH in minus TC in. Okay, from here Q dot maximum is 8.36 times with 70 minus 10. So you don't have to worry because Kelvin, when you want to convert Kelvin, then you will use this degree C can be cancelled out with the Kelvin value. Kelvin, okay. So you will get this value is 502 kilowatt. So now this is the maximum rate of heat transfer that this system can achieve, okay, for both hot water and cold water. Okay, for the cold water, it can be reduced up to 502 kilowatt. For the hot water, it can be increased. For the hot water can be reduced up to 502 kilowatt. And then for the cold water, it can be increased to the maximum of 502 kilowatt. Okay. Then from here, we have to calculate, in the question ask us about the outlet temperature for the cold and hot water. So for this limiting case, so what we have to do is we have to equate the equations of the Q dot here with the Q maximum that we get from here. So from that equation, so rearrange the equation. So we have Q dot equal to CC TC out minus TC in. Okay, from this equation we rearrange, we will get TC out because we want to find what is the TC out, and then TC in, so plus Q dot over CC equal to, okay, so substitute all the values, 10 plus 502 divided by 33.4 kilowatt per Kelvin. This is kilowatt. So please make sure that when you do this kilo in kilo, then you have to put this value in kilowatt also, so it can be cancelled out. Okay, if you use watt, then you have to convert this into watt value. Okay, times 10 to the power of 3. I hope that everybody will change it into watt. Okay, for this example or this tutorial, I will use kilowatt. Okay, to make you to simplify the calculation. Okay, so now we will get 25 degrees Celsius. And then what about the TH out? Q dot equal to CH. Okay, TH out, TH in minus TH out. So why does this arrangement of temperature for the hot water is in minus out? Because we know in much more greater or much more higher in terms of the temperature compared to the outlet temperature. Therefore, we have to subtract inlet temperature of the hot water with outlet temperature of the hot water. So you have to rearrange this to find what is the TH out. So your TH out equation will be TH in, okay, minus Q dot over CH. So 70 degrees Celsius plus, so this is degrees Celsius. Oh, sorry, not plus, minus, okay, 502 divided by 8.38. So you will get your TH out is 10 degrees Celsius. Okay, as you can see here, TC out can be reduced up to 25 degrees Celsius by using the maximum temperature here. Okay, TC out can be increased up to 25 degrees Celsius. And then for the hot water, it can be reduced up to 10 degrees Celsius. Here, the 10 degrees Celsius is the same as the temperature for the cold water. So from here, we know that we have calculating the Q dot maximum, and then the Q dot maximum is based on the heat capacity of the hot water. Therefore, in this equation, we are assuming that totally or the temperature will be reduced to the minimum value for the hot water. So that's why in your equation, you get your Q dot up to 10 degrees Celsius. It is the same as cold water because hot water is reducing or releasing the energy from the Q maximum. We know that we use CH as our heat capacity, and then CC we know that we have for about how much when we subtract 33.4 with 8.36, we have an excess. So that excess, that's why this temperature, this TC out, could not be reduced up to 70, could not be increased up to 70 degrees Celsius because our Q dot maximum is 8.36 because we are using CH as our heat capacity in the Q maximum. So if you chose CC as your heat capacity in the Q maximum, you will increase the temperature for TC out up to 70 degrees Celsius. And then for the Q dot, it will be in negative value. So which is impossible for the value of the Q dot for to reach up to negative 10 degrees Celsius. So that's why we are calculating the Q dot maximum by substituting this C minimum of C minimum heat capacity is the minimum heat capacity for the system. Okay, that's all for the Q maximum. Okay, thank you.